Okay students, we were discussing about magnetic dipole and magnetic dipole moment or magnetic moment, simply magnetic moment. How actually magnetic dipole moment is defined? Magnetic dipole moment is defined as a product of either of the pole strength and the distance between two poles. And in last class I already told you, I am comparing that with the electric dipole moment. There also we defined electric dipole moment, that P, how is that measured? Electric dipole moment is measured as a product of either of the magnitude of the charge of the dipole and the distance between two charges. Because there the electric dipole, it was defined as a system of two unlike equal charges separated by a certain distance. Here again, in magnetic dipole also, we define magnetic dipole also in the same way. Magnetic dipole is again a system of two unlike equal poles. Unlike equal poles, one pole will be north and other pole will be south. Both are of same magnitude, both are of same pole strength. But these two are opposite in their nature. One is the north pole and the other is south pole. By the properties of magnet, then it has been seen that it is not possible to have individual isolated pole. Only north pole cannot exist, only south pole cannot exist. But in electrostatics, there it is possible to have individual isolated charge, like only positive charge, like only negative charge. This all we did discuss in our last class. Magnetic dipole moment or magnetic moment is M is equal to, how is that measured? M is equal to product of the either of the pole strength of either north pole or south pole and the distance between two poles. That is called as a magnetic length. This already we have seen. And example for the magnetic dipoles, what are the examples, which examples we can treat them as a magnetic dipole? Bar magnet is a one such, which is a magnetic dipole. And solenoid, current carrying solenoid, that also is an example for the magnetic dipole. And electron revolving in its orbit around the nucleus, that current small tiny atomic loop, that also acts as a dipole. That also will have a two poles, north pole and south pole. These are all examples for the magnetic dipole. Now current carrying solenoid, already it is seen how actually current carrying solenoid is equivalent to bar magnet, because bar magnet will have a two poles, north and south. In the same way, current carrying solenoid also acts like a dipole, because that also will have two poles, north pole and south pole. To show you, I just took this plastic pipe. This you can compare by treating it as a current carrying solenoid. Solenoid means a long hollow cylinder on which a copper wire, insulated copper wire is wound. And such a long hollow cylinder, non-magnetic material, that cylinder is a non-magnetic material like a plastic, on which insulated copper wire is wound. When you send the current through all the turns of the copper wire, then that current carrying solenoid, it acts like a magnet by possessing two poles depending upon the direction of flow of current. One pole of that solenoid acts as a north and the other end of the solenoid acts like a south. And this also is an example for the magnetic dipole. This is what about we did discuss so far. Now today let us come to this magnetic field at a point on the axis of magnetic dipole. Magnetic dipole means, here I take a bar magnet. Bar magnet is a magnetic dipole, because that will have two equal poles of opposite nature, north and south, separated by certain distance. Here we are deriving an expression to find the magnetic field strength or magnetic field intensity. And I have been telling you that these all terms are nothing but the same. Which are the terms? Magnetic field intensity, magnetic field strength, magnetic flux density. All these are nothing but the same. But we commonly simply treat it as a magnetic field. Magnetic field means same. Field strength, field intensity, or flux density. All are nothing but the same. Here now, in this class, we are deriving an expression for the magnetic field intensity where at a point, where that point is on the axis of the magnetic dipole. Axis of the magnetic dipole means that is a straight line or the line which joins two poles of the magnet. That line is called as a magnetic axis. Now, where we are supposed to find the magnetic field strength? We are supposed to find the magnetic field strength on the magnetic axis of the bar magnet. On the axis of the bar magnet, and that axis of the bar magnet only is called as an axial line. Axial line. Let me take one bar magnet. Bar magnet means that is a dipole, magnetic dipole. A bar magnet of pole strength Qm. Let me take it as a south pole, and here another pole of the bar magnet, north pole of a same pole strength Qm. Both are opposite in nature. These two poles are separated by a distance 2l. Distance separated 2l between the two poles. This is called as a magnetic length. Center of the magnet, it is O, center of the magnet. This is now, this bar magnet, it acts as a magnetic dipole which will have a two unlike equal poles, north south of the same pole strength. Now we are supposed to find the magnetic field at a point on the axis of the magnetic dipole. Now I choose a point P. Let P be the point at a distance r from the center of the magnet. From the center of the magnet. Because at any point within the magnetic field, if you want to find the magnetic field strength or a field intensity, you just remember in electrostatics what we have done there. To find the electric field intensity at any point within the electric field, there we were considering one positive unit test charge, at which point we need to know the field intensity. At that point, we are supposed to imagine one unit test positive charge, and are assuming that unit test positive charge, how much force is experienced by that unit test positive charge at any point. That force experienced by the positive charge at any point itself is a field intensity at that point. A magnetic field irli electric field irli ಆ ಫೀಲ್ಡ್ ಅಲ್ಲಿ ಯಾವುದೇ ಪಾಯಿಂಟ್ ಹತ್ರ ನಾವು ಇಂಟೆನ್ಸಿಟಿ ಫೈಂಡ್ ಔಟ್ ಮಾಡಬೇಕಂದ್ರೆ ಅಲ್ಲಿ ಎಲೆಕ್ಟ್ರೋಸ್ಟಾಟಿಕ್ಸ್ ಅಲ್ಲಿ ಏನು ಮಾಡ್ತಾ ಇದ್ವಿ, ಯಾವ ಪಾಯಿಂಟ್ ಹತ್ರ ನಾವು ಇಂಟೆನ್ಸಿಟಿ ಫೈಂಡ್ ಔಟ್ ಮಾಡಬೇಕು ಆ ಪಾಯಿಂಟ್ ಹತ್ರ ಒಂದು ಪಾಸಿಟಿವ್ ಟೆಸ್ಟ್ ಚಾರ್ಜ್ ನ ಅಸ್ಯೂಮ್ ಮಾಡ್ತಾ ಇದ್ವಿ. ಆ ಪಾಸಿಟಿವ್ ಯೂನಿಟ್ ಟೆಸ್ಟ್ ಚಾರ್ಜ್ ಅಲ್ಲಿ ಎಷ್ಟು ಫೋರ್ಸ್ ನ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಮಾಡುತ್ತಾ ಅದೇ ಆ ಪಾಯಿಂಟ್ ಹತ್ರ ಫೀಲ್ಡ್ ಇಂಟೆನ್ಸಿಟಿ ಅಂತ. ಇಲ್ಲೂ ಅಷ್ಟೇ. Here also, if suppose this point P is the point which is considered at a distance r from where? From the center of the dipole, and at this point I want to know the magnetic field intensity. At this point I need to find the magnetic field intensity which is at a distance r from the center of the magnet. Now, to find the magnetic field intensity at this point, then in electrostatics, we were supposed to consider unit test positive charge, but here I need to choose a unit test north pole. A unit test north pole. Of course, it is known to us, it is not possible to have an individual isolated north pole, but we can assume. We can assume on comparing this with the electrostatics. This is the analogy we are studying or comparing that. Now, if you want to find the field intensity at this point P, we need to assume one test north pole, unit test north pole at this point P. How much force is experienced by that unit test north pole on placing over here at this point? That itself is a magnetic field intensity at this point P. How much force is experienced by the test north pole? That itself is a field intensity. And here I have taken that point P along the axis of the magnet. See, this is the magnetic axis. Magnetic axis is a straight line which joins or which passes through the two poles of the magnet. And this chosen point where the intensity is to be found, that is along the axis of the magnet, and here it is taken at a distance r from the center of the magnet. See, all the forces means gravitational force, Coulombian electrostatic force, magnetic force. These all forces are central linear forces. Central linear forces means which act between centers of two bodies. Which acts between centers of two bodies. That's why these all forces are called as a central linear forces. Electrostatic force, either of repulsive force or of attractive force. Here also magnetic force. That's why now the point chosen is along the axis, along the straight line. Force also acts along the straight line only because forces are central linear forces. Center of one body to center of the another body along the straight line. That's why these forces are called as a central linear forces. Okay, now if I assume one unit test isolated north pole here at a point P, that unit test north pole, if you imagine a point P, that is being repelled by this north pole. Because of this north pole of a source magnet or a magnetic dipole, imagine that a test north pole is repelled in this direction. This I can take it as a field at a point P due to north pole of the magnetic dipole, due to the north pole of the source magnet. This is a test magnet and this is a source magnet. Now, magnetic field is a vector quantity. Field at a point P due to north pole of the source magnet or magnetic dipole which acts along MP. Now, here is considered a bar magnet of a pole strength Qm, pole strength Qm, and the magnetic distance of a dipole, the distance between the two poles is 2m. If the magnetic dipole moment or a magnetic moment or a magnetic dipole moment is measured by the product of either of the pole strength, either of north or of a south pole strength of either of the pole into distance between the two poles, given into 2L. Remember, the electrostatics magnitude of the charge was taken as a Q. Here, to differentiate this pole strength from that charge, I am writing this as a QM, magnetic pole strength. This is again a vector quantity. There the electric dipole moment which was acting from negative to positive charge. Here this is a magnetic moment or magnetic dipole moment which also acts always from south to north. There it was negative to positive charge. Here it is south to north. Okay, this is of a magnetic dipole moment or magnetic moment. Now let me take this field at a point P due to north pole of the bar magnet. B1 vector is equal to mu naught by 4 pi by the definition. Magnetic field intensity or magnetic field is nothing but the force experienced by the unit test north pole at that point. This is magnetic field is a magnetic force experienced by the unit test north pole. And Coulombian law, by following the Coulombian law of magnetism, force, how can this be written? Force existing between two poles of the magnet is directly proportional to the product of the two poles. Directly proportional to the product of two poles, and inversely proportional to the square of the distance between them. Proportional to, if you take equal to, there comes constant of proportionality. That constant of proportionality here it is mu naught by 4 pi. And I have told you in last class the importance of this mu naught, that is called as a permeability. That is a degree of measure of a medium for the magnetic field lines. Degree of measure of allowance. How many lines are allowed to penetrate through the medium? That is called as a permeability. Degree of measure of allowance or admittance. Degree of measure of allowance or admittance of a medium for magnetic field lines. For magnetic field lines. That is called as a permeability. There in electrostatics, permittivity. There it was not admittance. There it was a non-admittance. Degree of measure of medium of non-admittance for the electric field lines. Non-admittance for the electric field lines. Here admittance for the magnetic field lines. We are treating this in a free space. Free space. That's why the constant 4 pi comes. Free space means 3-dimensional. 3-dimensional means volume. Whenever we have a 3-dimensional, we will have this 4 pi. If we have only 2-dimensional, there 2 pi comes. 2-dimensional, 2 pi. 3-dimensional, 4 pi. Volume, how is that measured? Of a sphere, volume is a 4 pi r cube. 3-dimensional. Like that. Here by following this, it's a definition of a magnetic field intensity, force experienced by the unit test north pole. Why only we take all the time north pole? Because the repulsive test is the surest test. Because magnet, if you take a magnet, this magnet can attract north pole of one magnet can attract the south pole of another magnet. At the same time, it is also able to attract materials like iron, nickel, cobalt. That's why attractive test can't be treated as a sure test. Which test should be taken as a sure test? Repulsive test should be taken as a sure test. Because if you take a south pole of another magnet nearby the north pole of one magnet, then we can't have a repulsion, there will be attraction. And at the same time, it also attracts other materials also. Iron, nickel, cobalt. That's why attraction can't be treated as a sure test. Repulsion is the sure test. Okay, by following this definition here of field strength or field intensity, magnetic field intensity at point P due to this north pole of the dipole can be written V1 is equal to mu naught by 4 pi Qm pole strength of this north magnet divided by square of the distance. Square of the distance means from the center of the magnet to the point of observation. From the center of the magnet to the point of the observation. Point of the observation means where the field is to be found. Point of observation means the point at where field is to be measured. We are supposed to find the field at this point P. That's why this is called as a point of observation. Now the distance between point of observation and the north pole of the source magnet, because force is exerted by this north pole of dipole on this test north pole. This distance we have to take. This distance is r minus L, because magnetic length is 2L from the center, that is a L. The total distance between two poles is 2L. From the center, it is a L. Now I need this distance from north pole of this dipole to point of observation. This is a r minus L. The distance is r minus L square. Similarly, the direction C. This is a vector quantity. Field is a vector quantity. This is the magnitude of field. Direction. If I place a north pole, it is repelled due to this north pole, because the like poles always repel, and the direction of the V1 is along NP. Direction of V1 is along NP from north to point NP. Now if I take a field at a point P due to south pole of this magnet, because magnet is a dipole. What magnet is a dipole? When I consider this now test north pole here, this test north pole is experiencing the net force, which is not only due to this north pole, which is due to forces by two poles, by this north pole and also by this south pole. Both these poles are offering their forces on this test north pole. B1 is force on this test north pole due to this north pole. At the same time, this test north pole is attracted by the south pole. When this north pole is offering a repulsion, at the same time, this south pole is trying to attract it, because this is the north and this is the south. Unlike poles always attract each other. When this north pole is repelling this just north pole, at the same time this south pole is attracting, and that field due to the south pole at a point P is given by B2 is equal to mu naught by 4 pi. Both are same pole strength. Both the poles of bar magnet are of same strength, Qm divided by square of the distance. Square of the distance means now we have to take the distance between south pole of this bar magnet to the point of observation where field is to be determined, where field is to be found. Now this distance from south pole of this magnet to point of observation, this we know. From the center of the magnet, point P is at a distance r. Extra from center of the magnet to this south pole, this is extra distance r plus L. Square of the distance between south pole to point of observation, r plus L whole square. Now two forces are acting on this unit test north pole placed at the point P. Now the net magnetic field. Now the net, or you can call it as the resultant magnetic field. Net magnetic field, field intensity is simply said as a field. Now the net magnetic field B at a point P due to both the poles of this dipole, due to both the poles, B1 field due to north pole at point P plus field due to south pole at point P. Any of this field is a vector quantity. Here the direction of this field, direction of the field at P due to south pole is in this direction. When this test north pole is repelled due to north, at the same time it is attracted by the south. That field is opposite to this. B2 is along PS. Along PS. Say now, this test north pole magnet is repelled due to north, at the same time it is attracted due to south. Finally, where will it move? That is the final resultant field what we require. That resultant final field is given by the vector sum, because these two are the vectors. Resultant vector of these two, net vector, the angle between these two is 180 degree. In vectors we have studied, if the angle is 180 degree, while finding the resultant vector of two vectors, if one vector is acting in this direction and the other vector is acting in opposite direction, A and B, if the angle between them is a 180 degree, then the resultant is given by the R is equal to square root of A square plus B square plus 2AB cos theta. Angle between them is 180 degree, because these two are acting in opposite direction. Cos 180 is -1. Then the magnitude of the resultant it will become R is equal to A square plus B square. Cos 180 is equal to -1. This will be -2AB. Finally, R is equal to square root of A minus B whole square. Square root will get cancelled. Magnitude of the resultant vector, magnitude of the net vector is equal to A minus B. This is we studied in PC first year itself, splitting up of a vector. I know you people could not remember, because you people have to be made to remember all the time. That's why for that I have to invest my time. That's all. Now come to this two vectors, how these two are acting. I have written symbolically vector sum to get the resultant vector, but actually the angle between these two vectors is 180 degree. That's why resultant magnetic field at a point P due to two poles of the bar magnet B is equal to B1 minus B2. B1 minus B2, and B is equal to resultant field is equal to B1 is, what is the B1? Here it is mu naught by 4 pi qm by R minus L whole square minus B2 is mu naught by 4 pi qm by R plus L whole square. On solving, it can be written mu naught by 4 pi is common, qm is also common, one minus r minus l whole square minus 1 by r plus l whole square. I am taking LCM of these two. I am taking LCM and I am rewriting this mu naught by 4 by r plus l whole square minus r minus l whole square divided by, I am multiplying these, not taking LCM. It can be written as a r square minus l square whole to the power of 2. If you want to write r minus l whole square into r plus l whole square, then multiply them. Finally, you will get r square r to the power of 4 plus l to the power of 4 minus 4r into l. On cancelling, on multiplying these two denominator terms, r to the power of 4 plus l to the power of 4 minus 4rl can be written as a r square minus l square whole to the power of 2, just like a minus b whole square. But here our a is r square, b is l square. Okay, to do that, given numerator also, we can simplify this. On simplifying, that, we will get b is equal to r square plus l square plus 2rl, r square plus l square plus 2rl minus a minus b whole square form, r square minus into plus minus l square minus 2ab minus 2rl, this minus that minus, it will become a plus 2rl plus r square minus r square plus l square minus l square, it will become a 4rl. mu naught by 4 pi into qm divided by r square minus l square whole to the power of 2. Finally, the expression is p is equal to mu naught by 4 pi 2rl 4rl. Don't get confused, r and l. 4rl 2rl plus 2rl, I write it as a 2 into 2 qm l into r divided by r square minus l square whole to the power of 2. See that 4rl, how it is written 2 into 2 into r into l. Why I have written like this? Because I need that product of either of the pole strength and the distance between two poles. This is nothing but the magnetic dipole moment. That's so that I can express magnetic field at a point P on the axial line due to dipole in terms of a dipole moment. That's why I am writing that. I need field intensity at a point due to dipole in dipole moment. That's why this will be mu naught by 4 pi 2. This is nothing but the magnetic dipole moment. Magnetic dipole moment is represented by this small m vector quantity into r divided by r square minus L square whole to the power of 1. See now, the resultant magnetic field at a point P on axial line is in terms of a dipole moment, in terms of a M. This is the final expression. For a short dipole, we have done this in electrostatics. For a short magnet means short dipole, whose length is very small. If you compare with this distance, if R is very greater on comparing with its length, it means our magnet is only of this much. You can imagine if it is of 2 centimeter, but we are measuring a point at some 20 meter away. Magnetic length is only 2 centimeter, but the point of observation where that point of observation is 20 centimeter away. It means that the distance R is 10 times greater than the length of the magnet. In such cases, this magnetic length, which is of only 2 centimeter, that is a neglect. On neglecting this L length in this expression, for short magnet, field at a point on the axial line due to short magnet is B equal to mu naught by 4 pi 2m. On neglecting L square, here it becomes 0. R square whole to the power of 2, R to the power of 4. In numerator there is a 1R. Magnetic dipole moment is a vector quantity. 1R will get cancelled with the 1R here in the denominator. The final expression is field intensity at a point P due to dipole B is equal to mu naught by 4 by 2m divided by RQ. This is a vector quantity. Even for this distance also you can take a vector RQ. In electrostatics also we have come across the similar type of expression. Electric dipole moment in case of magnetic dipole moment, electric field intensity in place of a magnetic field intensity. These are the changes. This will help you to remember. Okay, now see the direction. If I place this north pole here, test north pole, it is repelled and always it is away. Which is always resultant field is always from N to P, along N to P, along NP. It repels. Why always it is being repelled, this test north pole? Because this point P is very close to north. It is very close to north, and which is far away from the south. And magnetic dipole means that is a system of 2 poles of a same pole strength. North pole also will have a same strength, south pole also will have same strength. Now if I place this one test north pole here, this test north pole placed, which is placed at the point P, which is very close to north, and let us assume it will have some strength. Okay, but this south pole also will have the same strength, but which is away, far away from this point. What I mean to say, how much, with which force it is being repelled by the north pole, with the same force it is not attracted by the south. The force of repulsion is greater on this due to this north pole, because this north pole is close to this. With the same force, this test north pole is not attracted by the south pole, because south pole is far away from the point of observation. That's why resultant field is always along S, N, P. away from the target. Remember this.